So I'm going to take up the dipole interaction. Okay, dipole interaction. I will be deriving the general result. Okay, the force of interaction between the two dipoles in the general case, and for any specific case you will be able to apply that direct formula. Let's see. Okay, so here I can say, let's say that we have two dipoles. This is dipole of dipole moment T1, and then we have another dipole which is, this is the center of this first dipole, and at a distance r we have another dipole like this. I'm taking up any general case, and let me say this angle is given to be theta and this angle is given to be alpha. So r is this distance from the center of the first dipole to the center of the second dipole. R is this distance, and this alpha is, the dipole which is making with respect to this line. In, let's say here it is also anti-clockwise sense. So here I'm taking this theta and alpha both in anti-clockwise sense, and it is taken to be positive. Okay, this is our, and we have P1 and this dipole of dipole moment P2. So what are the given parameters here? Given variables are, we have given, what are given? Given we have P1, P2, R, theta and alpha. So this is the general orientation of any two dipoles, and we have to find force of interaction between these two dipoles. Okay, force of interaction between dipole 1 and dipole 2. So you have seen several problems, and in the most easy problem, you see, if we have this dipole and this dipole, both are in the same direction, what is the force of interaction? That comes out to be 6k P1 P2 by r to the power 4. Everyone knows, right? Where r is this distance, and it is attractive. And for any case we can have, okay, for any case. And this particular concept can also be applied not only to this electric dipole but to the magnetic dipole as well. For example, in place of this electric dipole, we have two permanent magnets. So the exact same way you can apply, exact same thing. We will see it later. As well as if you have to, for example, current carrying circular wire we have, and then there is another circular wire. What is the force of interaction between these two magnetic dipoles? Problems like this. So all these problems can be tackled using this concept. And I'm going to derive the general result, and I will suggest all my students to remember this. Okay, that is going to make your life pretty much easier. Otherwise, it will be very difficult in different cases. Again, you have to think from the basics, right? So how to approach this? How to approach in order to find the force of interaction between these two dipoles? That is going to be the topic. So one way is to think that force on the dipole 2, force on this dipole 2 due to the dipole 1 is equal to, everyone knows this, is P times, means dipole 2 P2 times del E upon del L. Okay, this is one way to find the force. Del E by del L is the directional derivative of electric field. And if I apply this concept, it is going to take, very complex mathematics will be involved. So I'm not going to take up this way. Rather, what my idea is, first let me find the potential energy of this dipole. Everyone knows that the potential energy of this dipole will be minus P2 dot electric field due to this P1. Okay, and once we have this potential energy, somehow we have to think of the force of interaction is nothing but negative of the gradient of the potential energy. So I'm not going to use this concept. Rather, I will be using force is equal to minus del U. This is the gradient, right? Minus del U. So this concept I will be using. And so many analysis will be there. Everyone knows that you can break this in x, y, z, and then it becomes fx equal to minus del u by del x, partial derivative of u with respect to x. Similarly, fy is nothing but your minus del u by del y minus del u by del z will be fz, like that. So the thing is how to have this force. This is the catch point here. We will go step by step. So the idea is I'm not going to use this, rather I will be using this one, this concept. So let me see. So I'm going to erase this. Let me do. Okay. So here, first of all, I am interested in writing the potential energy of this dipole. So P2 is, I'll be using U is equal to minus P2 dot the electric field at this point, P2 dot E. Okay, electric field at this point. Fine. So now, how to use this? How to take this dot product? Well, should I use like this X, Y and Z rectangular components? Should I use that rectangular coordinate system, or should I use the polar coordinate system? So in here, if I apply the polar coordinate system, it is going to be very, very helpful. Why? Just think, why? Because during the learning process, you should keep on asking why at each step. It's very important. Why I am doing this? Why not other way around? That is very important in order to get the understanding as well as feel of these concepts. Because here, if I take this, the center of this dipole as the origin, and then R, and we have the theta, right? So why not use this R theta? Why to go in terms of X? We'll be writing R cos theta is, X and R sin theta Y. I'm not interested in that. So rather I will be using the polar coordinate system, okay, in solving this problem. Well, so let me take this origin, and then you have this P2 and E vector. So why not to define the unit vector along R direction, along this radial direction, and perpendicular to this radial direction, you will be theta cap. So I'm defining one. In this case, I'm defining this as here. In this direction, I have R cap, and in this direction, I have the theta cap. Okay, and this is my theta at moment P1 like this. So naturally, P2 can be written as P2 is nothing but your P2 vector equal to, which is P2 cos alpha, and what is its direction? In this direction it is R cap, and similarly plus P2 sin alpha in this direction, and the direction is theta cap, like this. Direction is theta cap. So we have this P2 vector, and then the electric field. Electric field due to this dipole, in this direction you have to write, and perpendicular to this. So everyone knows what is the electric field of this dipole in the radial direction. So ER, everyone knows that, 2kp cos theta by r cube. Okay, so it will be writing, you will be writing 2, let me write it here. So ER equal to 2kp cos theta upon r cube, and p is due to the p1, so p1 I'm writing, and then we have the e theta. E theta is k p1 sin theta upon r cube. So ER E theta means while deriving the electric field due to the dipole, you must have used this ER and E theta, right? So in this direction we have the ER component, and then in this direction we have the E theta component, right? And we know this one. If you don't know this, you must know how to find this ER, because potential due to the dipole you know, which is kp cos theta by r square, and then ER is nothing but minus del v by del r, and E theta is nothing but minus 1 upon r del v by del theta. You might have remembered, okay? So we have this ER and E theta. So U can be written as, directly I can write, what is your U? U will be like this dot product. So the dot product means this times ER, okay, plus this times E theta. So it will be P2 cos alpha times 2k P1 cos theta by r cube plus P2 sin alpha times k P1 sin theta upon r cube. Okay, so we have this, right? So this is nothing but your potential energy V got, potential energy of this dipole due to the electric field created. And if I just, you have to simplify it, so you have to take this k P1 P2 upon r cube, okay, and then we have 2 cos theta cos alpha plus sin theta sin alpha. So this is our potential energy. which we have derived. Kp132 by Rq times this term. And in fact, they may ask you, what is the energy of interaction between these two dipoles? If they are asking, then you can have this. So better you can remember this result as well. What is the energy of interaction? For the general case, we have this, okay? Remember this, I have put the star over here. So using this U, I'm going to find the force. How to do that? Let's see. I'm erasing it, and I'm suggesting all my students to have the notebook. You should also, side by side, you should keep writing and then move on. And sometimes I'll be telling you to solve these equations. I'm not here to solve the equations, okay? Otherwise it's going to take long time, and our objective will be not fulfilled. So my main objective is to develop your analytical skill, not to do these equation solving and then getting the answer, okay? So we had our this dipole P1, and then we had this one. Let me write one more time. This theta, this angle is alpha. This is a P2. So energy of interaction between these two dipoles we have this one. I want to find the force. In this direction, I will have one component of the force, and in another direction, I will have another component of the force. So this I am calling is nothing but Fr, and this component is your F theta. Okay, Fr and F theta. So I am resolving this net force along the radial direction and along, the theta direction. It means the perpendicular to R. I am just resolving it. Why? Because I have this U. U is a function of R, theta and alpha. Okay, so I am interested in this direction as well, and is perpendicular to R. So how to get this Fr along the radial direction? So as we know that F vector is nothing but the gradient of the potential energy with a negative sign. So in this case, I can say that you can also write this way. If you go in this direction, what is the displacement? This displacement is going to be dr. And if you go in this direction, perpendicular to this, what is this displacement? Because this angle is d theta. So this is r. So this is r d theta, right? So if you are going in this direction, keeping theta constant, so you can easily write Fr, which is the radial component of the force, is nothing but minus of the del u upon del r, keeping theta constant, right? Because you are moving in this direction. And similarly, if you are moving along theta direction, in this direction, perpendicular to r, keeping r constant, right? Because r is constant, and in moving d theta, you have this same r like this. So you'll be writing F theta is nothing but minus del u by, and what is this displacement? Is r d theta, right? So this becomes your del theta into r. So I'm writing this way, 1 by r del u by del theta. This is keeping r constant, and here we have this theta constant. Here theta is constant, and then we have r equal to constant, right? So now we have this known. It's just like, the electric field in radial direction is negative of the gradient of potential along r direction. And similarly, the electric field in theta direction is minus 1 by r del v by del theta, where v is the potential, while calculating electric field. Similarly, while calculating force also, you can write like this. Fr is nothing but negative del u by del r. F theta is negative 1 by r del u by del theta. Well, now everything is just the, steps of these taking derivative and nothing more. Just simple mathematics is involved. So the physics part is done over here, and then simple mathematics is there. You have to take the derivative. Fr is minus del u by del r. Let me take, means here theta, alpha both are constant. So again, Fr is nothing but it's constant, just taking the derivative of this. So I'll be taking the derivative of r cube 1 by r cube with respect to r. So I'll be getting minus 3k p1 p2 upon r power 4, and the remaining term is as it is. 2 cos theta cos alpha plus sin theta sin alpha. Okay, this we are getting our Fr. And you have to remember this as well. I'm putting double star. It's very important. Fr means now we got this radial component of the force. Similarly, F theta will be minus 1 by r del u by del theta. Now you have to differentiate u with respect to theta, keeping r constant. R is constant. So this term will be constant, and you have to differentiate this. Well, now one more thing I have to tell you. Here, is alpha constant? Yes or no? No, alpha is not constant. Alpha is not constant, because as you move, in theta direction, in this direction if you are moving, then in that case with respect to, because this line is heading right, so with respect to this, alpha will be, alpha will be this angle, so this keeps on varying. However, I can say that the dipoles are fixed. This arrangement of the dipole is not changing. This dipole is, let's say, along positive x direction, it's along this direction, any arbitrary direction. So these two dipoles are fixed. So if these two dipoles are fixed, what does it mean? It means if this angle is, theta, so this angle is also theta here, over here, this angle is also theta. And if this angle is theta, so now this dipole is fixed, it means the direction of this dipole will be alpha plus theta, right, this angle. So alpha plus theta is going to be constant. Okay, alpha plus theta is constant, not the alpha. So I can also say alpha plus theta is constant, and now if you have to take the derivative of u with respect to theta, then you have this term del alpha by del theta plus 1 equal to 0. It means you'll be getting del alpha by del theta equal to minus 1, keeping this term as constant. So if you differentiate this, you'll be, you have to apply the product rule to differentiate this. And similarly apply the product rule to differentiate this term, because these two terms are there. And after you solve, I'm going to write the direct result over here. And I suggest all my students to differentiate u with respect to theta. So finally, what will be f theta? So f theta is going to be minus 1 by r term times this. So f theta will be equal to minus 1 by r. It means I'm multiplying this, so it becomes minus k p1 p2 upon r power 4, and derivative of this. Okay, so how to take this derivative? I've already told you, like take the product rule and then solve this. So I am just writing the direct result. And what is this direct result? So remember, here it was 3, right? Here also it will be 3. So minus 3 k p1 p2 by r power 4 will be there, and then sine of, you will be getting theta minus alpha. After solving this, after taking the derivative of this term with del alpha by del theta equal to minus 1. And I want all my students to solve this and get back to me. So this is my f theta. I am boxing it and putting the double star. So now we have our final results. Let me erase this. We have our final result as fr and f theta. And it is easy to remember as well, because this term is constant. You have to remember this term for fr, and f theta is sine of theta minus alpha. And in fr, you have this term, right? 2 cos theta cos alpha plus sine theta sine alpha. And we have these two components of the forces. So we have the net force on dipole 2 due to dipole 1 is nothing but this force is fr, and the unit vector is r cap, plus f theta, the unit vector is theta cap. That's it. Which is the magnitude will be square root of fr square plus f theta squared. Okay, that's all about the force of interaction between these two dipoles. Now let's take some of the examples, simple examples, in which we have to apply this fr and f theta. And let's see. I have boxed it, you have to remember these two components. Let me take the simple case. This is case 1. We have P1 and this dipole is P2. What is the force of interaction between these two dipoles? R is the distance between them. So similarly, first you have to identify what is your, because r theta alpha, right? So what is your theta? Theta is obviously 0 degree here. And then what is alpha, by the way? Because alpha is also 0, you see, in this direction only. So alpha is also 0. And finally you have to put in your final result. So you see this theta alpha sine, this will be 0, sine 0 0, f theta will be 0. So f theta is coming out to be 0. And what is your fr? In your that formula, you put that minus 3k p1 p2 by r power 4 into 2 cos theta cos alpha, which is 2 cos 0 cos 0 1. So 2 plus sine theta sine alpha, sine 0 sine 0. So 2 plus 0, which comes out to be minus 6k P1, P2 upon R power 4. This is your F1. F theta is 0. So, in which direction the force is? Negative sign is here. Negative sign shows that along minus R cap. So, on dipole 2, the force of interaction on this dipole 2, the force will be in this direction. So, attractive force will be there. This is your FR, right?